Hello everybody, welcome to today's class in physics for standard 9. Let's talk about Newton's laws of motion. Well, in our last few chapters we discussed about motion and the equations of motion. We did a few calculations on that as well. Today let's look at what the laws that govern motion and specifically Newton's first law. So before we go into that, there are a few things that we have to brush up. So I want you to give me an example for a balanced and unbalanced force. I'm going to give you a second to think about it. Well, if you look behind me, you can see two cars playing tug of war. Now, the two cars are pulling in opposite directions and their engines are running. The wheels are spinning as you can see. But the rope is not moving. The center of the rope is still. Does that mean there is no force acting on the rope? Well, not exactly. There is force acting on the rope, but it's just that it's equal forces to the opposite sides. So there's a total net effect of zero. So a balanced force is any force where the net components of the force add up to give a zero effect. So there are forces acting on it, but they cancel each other out. That is an example for a balanced force. Now, imagine that this car starts to win and suddenly this car pulls away very strongly and wins the game. So that means this car has applied a greater force in the other car and therefore the rope has moved. This is an example for an unbalanced force. That is, the force of 400 Newton applied by this car is greater than the 300 Newton that is applied by the other car, and therefore this car has won. Now there's a net effect of 100 Newtons in the center of the rope. Here, unlike earlier where both forces got cancelled out, here this force being greater manages to win over the other force. Now, we know these two forces and I hope you've all clearly understood. I want you all to think of another example in your mind as we proceed. Now, we all know Galileo as the father of modern science. He's made a lot of contributions to science as a whole. Experimentation was his thing. He made the telescope and he always made it a point to test everything that he heard. He would not believe anything until he saw it for himself. And that is what made him such a great scientist. Now we'll look at one of his experiments from his olden days. So he took a slope and a ramp and he put them close together. Now he made sure the slope and this ramp was perfectly smooth. So he lubricated it. He took sandpaper and sanded it down. He made it like as frictionless as he could. Now he took a ball and he placed it on top of the slope. And he proceeded to give this ball a small touch. And he saw that the ball will roll down, reach the bottom, roll up, and then roll back down. So he noticed this, he repeated this a multiple number of times, and he noted h1, that's the height from which he released the ball, h2, the height which the ball reached. He also looked at the time taken for the ball to complete one oscillation. He looked at the distance that the ball had to cover. He also calculated things such as the velocity of this ball. Then he repeated this experiment a couple of times. Maybe a few more than a couple, but yeah, he made sure that his readings were correct by repeating this experiment multiple times. Now, he moved on to the second experiment. That is, he took the slope that was there in the earlier experiment. He took a ramp which is longer but was less steep. Now he's put them two together and he's observed the ball rolling down and rolling back up. And he did this also a countless number of times, where he proceeded to measure h1, that's the same height as before, h3, that's the height of this ramp, then there's distance d, time taken, and so on. He also looked at this length that the ball had to travel. He also calculated the velocity and many other things. So he repeated this also a lot of times. Now, he then proceeded to the third experiment. Again, same slope as before. The ramp again was longer than the second one as well, but it was less steep again. Here also he did this experiment a lot of times. He measured the variables we discussed earlier. They were the height from which the ball was dropped or released, That's h1, the same for all of these experiments. h4, that is the height this ball reaches in this slope. He goes on again, distance here, the time taken, the velocity, this traveled path length, and so on. Again, a multiple number of times this was repeated, and he did that as well. Now, he took a ball from a height h1, same ramp. He released it from the top. He wanted to know what would happen if there was no ramp on the other side for the ball to climb up. Now, he watched it and he saw it kept on rolling for a long time before it came to a stop. He repeated this also a lot of times. Now, there was a pattern developing here. He noticed that the balls were going up and coming back down in the first three, but there was nothing there in the fourth one. So, in his experiments, he saw that h1 and h2 were equal. That is, the height the ball was released from and the height it reached were equal. That is, h1 is equal to h2 for the first experiment. Now, he went on to the second one and saw that h1 and h3 were also equal. That is, the height released and the height reached were the same. Now, even in the third experiment, he saw that his h1 and his h4 were equal. That is, h1 equal to h4. So, now we see a pattern developing here. That is, the height the ball is released from, it has to reach that same height when it comes to a stop. So, it doesn't matter how long it has to travel, because this path length is much less than this, and that again is much less than this. So, it's not about the distance the ball has to travel, but the height it has to reach before it comes to a stop. He saw this in all three of his first experiments. But he also noticed that in experiment 4, there was no h5 that was equal to h1. But the ball came to a stop anyway. This was confusing for him. Now, he did not understand why this happened. Then he went into thought and he realized that no matter how hard he tried, there's always going to be friction between this floor and the ball. And eventually the friction would cause the ball to stop. Now, he then hypothesized that if there was a perfect slope with no friction whatsoever, and this ball would roll down that slope, it would keep rolling for infinitely long time until it came to a stop. That is, it never stops because it can never reach the height h5, which is equal to h1. Now, after Galileo did this, let's do a question related to this as well. The question is, consider this first diagram, the diagram we saw earlier. Here, h1 and h2 are both 3 meters. The length of the base is 8 meters. The slope and the ramp touch the base exactly in the middle. Now, the acceleration felt by the ball when the ball rolls down is 4.9 meter per second square. We have to find three things in this question. That is, 1, the total distance traveled by the ball. That is, the distance traveled down and the distance traveled up. Then the velocity of the ball at the bottom of the slope. So, when the ball rolls down the slope, it stops there. What is the velocity there if we paused it exactly at that point? And third, what is the time taken for the ball to go all the way down and all the way back up? Let's look at this one by one. So, for any problem related to physics, it's always good to draw a diagram. We shall do that here as well. So, this is the ramp and slope setup. So, we know that this base is 8 meters and it is cut exactly in half. So, that would be 4 meters here and 4 meters here. Now, we know that the height was given as 3 meters and both sides 3 meters. Now, we know that this ball was released from here and it had an acceleration of 4.9 meter per second square. Now what do we have to find? One is the total distance traveled by the ball. So always when you do problems, note everything down before we start attempting the problem. So we know that this ball rolls down, reaches the bottom, then rolls back up and reaches the top. So the distance we have to find is this length of the hypotenuse of the two triangles we can see here. Now, if we know that this is a right angle triangle, we know the Pythagoras theorem, which states that the hypotenuse is always equal to the root of the squares of the two sides. That is 3 square plus 4 square. Now, what is 3 square? Anyone? Yes, it's 9. So that's root of 9 plus 4 square is 16. Therefore, 9 plus 16 is 25. And we all know the root of 25 is 5. So we found that this length is 5 meters. Now that's the answer to the first question. Now, we know that this length is 5 meters. Now we have to look at the other triangle. But we know that this is 3 meters, this is 4 meters. On the other side, this is 4 and this is 3. And both these angles are right angles. So, by the SAS theorem of congruence, these two triangles are congruent. Therefore, this side is also 5 meters. And the total length we have to find is 5 meters plus 5 meters. That is 10 meters. Now, let's move on to the second part of this question. That is, what is the velocity of the ball at the bottom of the slope? So, if we draw a line here, when this ball reaches its bottom, what is the velocity? Now, earlier class, we learned that v square minus u square equal to 2as. Now, s is the distance, a is the acceleration, u is the initial velocity, and v is the final velocity. Now, if we look at this diagram, we can easily see that s here would be the 5 meters that it has to travel, and u is 0 because the ball is at rest when we look at this experiment. Now, we know that this is 0, we know that this is 5, and the acceleration or a that we have to find is given in the question as 4.9. So therefore, v square minus 0 is equal to 2 into 4.9 into 5, and that is equal to, anyone? Yep, that's 49. So v square minus 0 is 49. Therefore, v square is 49 and v equal to root of 49, which is equal to 7, or the ball is traveling at 7 meters per second at the bottom of the slope. Now, we have to find the time taken for this ball to go from the top of this slope down to the bottom, then go all the way to the top of the ramp. So that is, we have to find the time t. Now, this time t can be split into two parts. That is the time taken from the top to the bottom and the time taken from the bottom to the top. That is equal to t1 plus t2. Let's first find t1. Now, we know that u is 0 and v is 7. Therefore, the average velocity, let's call it v average, is equal to 0 plus 7 by 2 is equal to 3.5 meters per second. So we have the velocity. Now, what is velocity? It is distance by time. So that is distance by time equal to 3.5, or we know that the distance is 5, so we take it to the other side. We have 5 divided by 3.5 is equal to t, which is, if anybody has got a calculator, I'd suggest you try this out. You can find that it is approximately 1.4 seconds. Now we found T1. Let's now look at T2. Now, if you have to find T2, that is the time taken for the ball from the bottom to the top. For this, we know that V is equal to U plus AT, or here we know that U is 7 because we found out the ball reaches the bottom at 7, so it starts going up again, the velocity of 7. So V is equal to 7 plus, now A. What is A? Why does the ball accelerate? It's due to gravity. And we know that if it's rolling down, it has a positive acceleration down that way. Then if it's rolling up, it'll have a negative acceleration because the gravity is pulling it back. So we put the opposite sign for the 4.9 and we have negative 4.9. Now T. This is the value we have to find. This T is T2. Now V is the velocity of the ball at the top. Can anybody tell me what that would be? You are right. That's 0. Now, this is a simple equation that we can easily solve. We have minus 7 equal to minus 4.9 T, or T equal to 7 divided by 4.9. Do this in your calculators, you'll find that this is also 1.4. Now, this is quite obvious because we found the first answer to be 1.4 and we know that these two triangles are symmetric, so this also has to be 1.4. Therefore, the answer for the third question is 1.4 plus 1.4, that is equal to 2.8 seconds. I hope you've all understood this problem. We've looked at this problem in a different way. We've covered quite a few topics as we've gone along. Now, let's go back to our lecture. We've discussed this, and after Galileo, there came somebody else. Probably a man that's smarter than Galileo and the smartest man to have ever lived, in my opinion. This man made the single most difficult part of mathematics, that is calculus, on a summer day. It took me years to learn this part of mathematics, and this man made it in just 3 months. Shows you how smart he was. And that too in a long time ago, in the 17th century, when science was not even as developed as it is today. He had no calculators, no computing power, nothing. He worked purely on pen and paper. Now, he saw Galileo's experiment of the ball rolling, and the Galileo saying that balls would roll forever if there was no ramp for it to climb up after it drops down from the slope. This was, in contradiction with the notion that was going around that objects like to remain at rest. So back then, everybody believed that objects like to remain at rest no matter what. And if it's moving, it will want to come to rest. But because of this contradiction of Galileo's experimental evidence and the contemporary notion or thought going around, he did his own experiments and calculations that are beyond our scope. But he reached at a conclusion that Galileo was correct. And he also made laws based on that. So his first law is directly related to Galileo's experiment and says that every object will remain at rest or uniform motion along a straight line unless it's compelled to change that state by the action of an external force. Now, what do you understand from this? Objects remain at rest or uniform motion. It means it doesn't have a preference for rest. It can be at rest or it can move. It doesn't matter about that. All that matters is it likes to remain as it is. So if it's at rest, it likes to be at rest. If it's at motion, it likes to be at motion. And you have to apply an external force. Now this is where the balanced and unbalanced forces that we discussed earlier comes into play. It has to be an unbalanced force acting on the body to make it change its original state. Now, since we've looked at this, I want you to remember something else. You've all learned about inertia in earlier classes. Now, does this look quite similar to inertia? Well, Inertia says objects like to remain as they are, and this says an object remains at rest or motion unless somebody makes a change. So therefore, it does look quite similar. Now, that's because this is where the term inertia comes from. So inertia is just direct effect or implication from this law, and that's why this law is also called the law of inertia. Now let's look at the three different types of inertia. The first one is inertia of rest. Now, for inertia of rest, we can look at this example. You keep something on top of a glass jar or a cup or whatever, and you flick the base off, and you can watch an object fall down. This can be done easily with, say, a cardboard and a coin. Now, this setup is quite complex, but you can easily try it with a cardboard and a coin. You put a cardboard sheet on top of a glass, put a coin on top of that, and you flick it, and you can watch it fly away as the coin falls into the glass. Now, this is due to the inertia of rest of the coin, or in this case, the egg, because the egg wants to remain where it is while the rest of the things move away. So it remains at rest there. It doesn't want to have the motion on the direction of this object. So as it moves away, the egg falls down into the water. Another example, something that we are all used to, would be us sitting in a bus or a car or a train or any moving vehicle. So now, when the vehicle is at rest, we all feel like we are at rest as well. Suddenly, when the vehicle starts moving, we have a tendency to move backwards. Now, why are we moving backwards? Have you ever thought of that? The answer to that is quite simple. It's because we want to stay where we are, but the car moves forward. So as the car moves forward and we remain at rest, our inertia of rest keeps us there, and we feel like we're falling backwards. It's not that we are moving back, it's just that we are remaining in place as the car moves away. Now let's look at the second example, that's inertia of motion. Now this is the exact opposite of inertia of rest. It is that objects like to remain in uniform motion. Now we fill a cart full of balls and we let it slide down a slope. It hits the brick and we see that the balls fly off. Now this is due to the inertia of motion of these balls. Balls want to continue in motion. There's a sudden stop, the box stops, but the balls keep moving along that same direction and they keep bouncing and going away. So this is the tendency of objects to remain in motion unless they are stopped by an external force. So we've looked at both the inertia of motion and inertia of rest. Now, this example we've already talked about in our earlier discussion, that is the car moving. So instead of it starting, now when it stops, we tend to go forward. The exact same reason, we have the tendency of going forward while the car comes to a rest. Our inertia of motion keeps us going forward. That is why I feel like falling over when you're standing on a bus and the bus stops suddenly. Let's talk about the inertia of direction. Now this is a bit more confusing for most people and it's not as easy to understand. We've looked at Newton's law. It says objects like to remain at rest or uniform motion, and the inertia of rest and inertia of motion explain those two things very easily. But this part, that is, objects like to remain in a straight line. This seems a bit confusing for most of you. Let's look at it. Imagine you're sitting on a bus and the bus is going around a curvy road, mostly in a mountain range of some sort. And as the bus turns, we see this tendency for us to go to the other side. So if the bus is turning left, we tend to go right. If the bus is turning right, we tend to go left. Now this tendency is not us going left or right. It's just that we want to continue in motion along a straight line. Now the bus is changing its direction, but we are continuing in our straight direction. So because you're moving in a straight direction, we have this tendency or feeling of moving to the other side. It's just the bus pressing against us more than us going to the opposite direction. Now this might be a bit complex. We'll come back to this in the next class as well. Now that is all for today. In our next class, we'll be talking about the second law of motion and looking at the equations of motion as well. Have a nice day and stay safe. Thank you.